All right, so here comes the fun part. Acid-base properties of a salt solution. And so it turns out that, I know you probably never thought about it before, but if you have thought about it, you probably think, well, salts are neutral because they are the result of an acid-base reaction. Remember, our acid-base reaction, we have an acid, a neutralization reaction, an acid plus a base gives us a salt and a water. So, since it's called a neutralization reaction, we tend to think of salt as being neutral, but this isn't always true. So let's just refresh our memory. What is a salt? Well, remember that a salt is an ionic compound. The positive ion can be any ion that is not H plus, and the negative ion of the salt will be any ion that is not OH negative. So you remember that an acid, we get the positive ion from the base. So like NaOH, we get the Na plus, and then we get the negative ion from the acid. So the problem is that if we have some negative ions that come from weak bases, weak acids, or if we have some positive ions that come from weak bases, then our salt can be acidic or basic. So that's what we're going to be talking about. So here's an example. NaCN, sodium cyanide. So NaCN is a salt, and you can go back to your solubility rules. So we know that NaCN will dissolve. Anything with Na will dissolve. NaCN will dissociate into Na plus and Cn negative. All right, so the question is, though, when we look at these ions, will they themselves react with water? They're the result of an acid-base reaction that may have happened just now, or it may have happened a long time ago when we get the salt. But what happens if we have Na plus and Cn negative in solution? Well, it turns out Na is pretty benign. It doesn't do anything. But the Cn negative actually can react with water because Cn negative is a weak base and can accept an H plus to become HCN. It's the conjugate of a weak acid. If you measure a 0.1 molar solution of NaCN salt, it turns out to have a pH of 11.1. So clearly it is a basic solution. It's not neutral. And so let's look at this a little more closely. Why is that? So again, the sodium ion is unreactive with water, and we'll talk more about this in a minute, but it turns out that because the cyanide ion is the conjugate of a weak acid, it will react. Remember, a weak acid doesn't really like to give away its H plus very much. So if you have the conjugate of a weak acid, Cn negative, it's pretty willing to accept an H back because remember, it's this tug of war for an H plus. So Cn negative hanging around in water will grab an H plus from water to form HCN and OH negative. Okay, so this was what happens when we have the conjugate of a weak acid. It will react with water to form OH negative, and your solution will be somewhat basic. Again, Cn negative is a weak base, and it's the conjugate of a weak acid. So actually, it's probably a little bit stronger base than HCN is an acid, and so the equilibrium shifts to the right, and we do have OH negative hanging around. And as you see, OH negative is a product, and so you would expect this to have a basic pH. The reaction of Cn negative ion with water is referred to as the hydrolysis of Cn negative, so it's reacting with water, the hydrolysis. Okay, so the hydrolysis of an ion is just the reaction of the ion with water. Now, if the ion is a base, then it will produce the conjugate acid and a hydroxide ion. If the ion is an acid, it will produce the conjugate base and the hydronium ion. So in our example, Cn negative hydrolyzes to give us the conjugate acid and the hydroxide ion. Because Cn negative hydrolysis is an equilibrium, we can actually write a Kb expression for it, which we will do in just a little while. So here's an example of an ion that acts that acts like an acid. So NH4 positive, when it's hanging around in water, it's willing to give up an H plus to water to form NH3, ammonia, and H3O plus. So again, NH4 positive is part of a salt. It could be NH4Cl or whatever. It's the ion from a salt, the positive ion from a salt that hydrolyzes to give its conjugate base and the H3O plus. And in a similar way, because it's acting like an acid, we can actually write the Ka expression for it, which again we'll do in a little while. So, first of all, let's see, how can we predict whether a salt will be acidic, basic, or neutral? Well, it all goes back to those strong acids, strong bases. If you can identify which acids are strong and which acids are weak, and then which bases are strong and which bases are weak, you should be able to predict whether a particular salt will be acidic, basic, or neutral. All right, because we know that we have this inverse relationship between an acid and a base pair. If an acid is stronger, it will give up an H plus. If the base is stronger, it will accept an H plus. Now, the anions, the negative ion from a weak acid, is a good base, right? With the opposite effect. So, and think about that. So let's say we have a strong acid like HCl. HCl is really willing to give up that H plus. So Cl negative is actually a very poor proton acceptor because it doesn't want the H back. If HCl really willing to give away the H plus, Cl negative is not willing to give it back. But a weak ion, like we talked about just a minute ago, Cn negative is a weak acid. HCN is a weak acid, so it's not really willing to give up that H plus. So on the reverse side, the Cn negative is fairly willing to accept the H plus because it didn't want to give it away much in the first place. So the anions of weak acids are fairly good bases. So the anions of weak acids tend to be basic because they're willing to accept an H plus from water, leaving OH negative as a product. So Cn negative is an example of this. So like I was saying a minute ago, the anion of a strong acid is actually a very poor base. So remember, a strong acid is a really, really good proton donor. So if it's really good at giving away the H plus, it's not very good at getting back the H plus. So the negative ions of the very strong bases have no basic character at all. Or what that means is they don't hydrolyze, they don't produce any acids or bases when they're dissolved in water. So an example of that would be Cl negative, because Cl negative is the conjugate of the strong acid HCl. So Cl negative, if it appears in a salt, you can pretty much ignore it because it does not hydrolyze with water at all. So just to review, those 6 strong acids, there's actually one little quirkiness. Those 6 strong acids, we have HCl, HI, and HBr. Those are 3 of them. So that means Cl negative, I negative, and Br negative do not react with water. So you can ignore them when they show up in salts. And then the other strong acids, HNO3, so NO3 negative, you can ignore in salts. ClO4 negative, the negative ion from HClO4, ClO4 negative. Now the one quirkiness is HSO4 negative, because it actually is a fairly strong acid itself. You can't count that. So it's actually those 5 negative ions. If they appear in a salt, they're going to have no basic character at all. So the cation of a weak base then is acidic, NH4 plus being an example of that. So again, if you have a weak base, something like NH3, it's not a very good proton acceptor, which means that its conjugate is a fairly good. Now we're not talking any of these being really strong, but on the relative scale, if NH3 is a poor proton acceptor, then it's a fairly good proton donator. NH4 plus then would be a fairly good. Its conjugate would be a fairly good donator. The cations of strong bases, however, just like the Cl negative, the anions of a strong acid, the cations of a strong base, again, virtually no acidic character because they just don't hydrolyze. It's just like it's the same thing. If they're willing to break apart from that OH negative doesn't want to grab an H from, there's no acid, then it's a little bit harder to picture this, but any positive ion that comes from those 6 strong bases, so let's review those. So Na plus, K plus, Rb plus, Ca plus 2, Sr plus 2, or Ba plus 2, any of those 6 positive ions from the very strong bases you can ignore when trying to figure out if a salt is acidic or basic. They basically don't hydrolyze, so you basically ignore them. So what we can do then is pull apart the salt and look at the 2 ions. Look at the positive ion. If the positive ion is one of those 6 that I just named, Na, K, Rb, Ca, Sr, Ba, if it's one of those, we basically ignore them when we say, well, no, that's neutral, so we can ignore them. And then we can do the same thing with the negative ion. If it's Cl negative, Br negative, I negative, HSO4 negative, NO3 negative, or ClO4 negative, again, we can ignore them because they don't hydrolyze. But other than that, we have to consider all the other ions. All right, so let's consider potassium acetate. So let's pull it apart and look at each ion separately. So we look at the K plus and think about, where did the K plus come from? Did it come from a strong base or did it come from a weak base? It came from a strong base. So what does that mean? It doesn't hydrolyze. The K plus itself does not hydrolyze. We can ignore it. It has no acidic character at all. Now we have to consider the acetate ion. So the acetate, C2H3O2 negative, is the anion. You go back, add the H plus back to it, so HC2H3O2, and you look at that and you say, is that a strong acid or a weak acid? Well, acetic acid is a weak acid, which means its conjugate base is relatively strong, and so it does have some basic character. So again, the negative ion of a weak acid has some basic character, and here they're showing you the reaction. C2H3O2 reacts with water, grabs the H, and you get OH negative. So it does have basic character. So potassium acetate, you can take, okay, it has no acidic character, but it does have basic character, so this salt will be somewhat basic. So we predict this to be basic. So as a summary, to predict whether a salt is acidic, basic, or neutral, and these rules apply to normal salts in which the anion has no acidic hydrogen, and that refers to what I was saying earlier. HSO4 negative doesn't really count here, so it actually has some acidic character as well. So a negative HSO4 will not be included in these rules. First of all, if you have a salt that has where the positive ion comes from a strong base and the negative ion comes from a strong acid, the salt has no hydrolyzable ions, and so we'll have a neutral aqueous solution. An example of this is NaCl. A salt that has the positive ion from a strong base, Na plus, K plus, Li plus, Ca2 plus, Sr2 plus, Ba2 plus, and the negative ion from a weak acid will have, the negative ion will have some basic character, and so this will have, this salt will be a basic solution. An example of that would be NaCN negative, where the Cn negative is the negative ion of a weak, that comes from a weak acid. A salt of a weak base and a strong acid, so if the positive ion is something other than those 6 strong base positive ions, Na, K, Li, Ca, Sr, Ba, and then if you have the negative ion from a strong acid, so Cl negative, I negative, Br negative, NO3 negative, ClO4 negative, those will have, the positive ion will have some acidic character to it, and so overall that salt will be acidic. An example of this would be NH4Cl. Another example it may be something like copper chloride, CuCl2. So even if it's just a regular metal ion, that's not one of the 6 positive ions, that it will still also be somewhat acidic. Now, if the positive ion comes from a weak base and the negative ion comes from a weak acid, we have a little bit of trouble because we don't know which one they're both going to hydrolyze. They're both going to have some character, either acidic or basic, and so it will depend on which one is stronger. And I will admit that I won't put one of these on the test. They're not super hard, but they can get confusing. So the main thing is that you have to compare the Ka from the cation with the Kb from the anion. If the Ka of the cation is larger, the solution will be acidic, and if the Kb of the anion is larger, the solution is basic. Although it's not quite as straightforward as it might seem, because, and we're going to talk about this in a minute, you can't just look up the Ka of the anion. I'm sorry, you can't just look up the Ka of the cation or the Kb of the anion. You have to kind of do some more calculations. So it is a little more complicated, but this is basically you get the gist of it. Whichever one is a stronger acid or base will kind of take over, and the salt will have that character. Like I said, I won't put that on the test. Okay, so if you want to try to find the pH of a salt solution, what you would need is to have the Ka of the cation or the Kb of the basic anion. Well, that's and I was sort of talking about that just a minute ago when you were comparing which ion was stronger by looking up the Ka of the cation or the Kb of the anion. And unfortunately, they're not listed directly in tables. And so it's not super hard, but it's not as easy as you might first think. But it turns out that the Kb for a negative anion is related to the Ka for the acid. They're directly related to each other. And so you're not going to be able to find the Cn negative, for example, the Kb for Cn negative, but you'll be able to calculate it by looking up the Ka for HCN. So it is a little bit more complicated. So let's look at what is the relationship between Ka and Kb. So here we have the first equation is the acidic HCN plus H2O gives us H3O plus Cn negative, and we know we can look up the Ka value for that. And then the Cn negative, acting like a base, reacts with water to give us HCN plus OH negative, and a Kb is the relationship there. So we would have HCN times OH negative divided by Cn negative would give us the Kb. All right, so now if we look at these two equations, and we've done this before, let's add the two equations together. And if we do that, notice that the HCN cancels on both sides, the Cn negative cancels on both sides, that we end up with 2H2O gives us H3O plus OH negative. Well, that's a familiar equation. That is just the ionization of water equation, and the K for that expression is just the Kw. Now, if you remember, when you add two equations together to get a third equation, the K values are related by multiplying. So if we multiply Ka times Kb, they should equal Kw. All right, so there is the same thing. So Ka times Kb equals Kw. And so if you're able to find, you can look up the Ka for HCN, and when you do that, you can find the Kb by using this equation. Remember, Kw is 1 times 10 to the minus 14. So if you have a salt where only one of the ions hydrolyzes, that would be either you have the positive ion from a strong base and the negative ion from a weak acid, or the negative ion from a strong acid and the positive ion from a weak base. So this doesn't include that fourth situation where you might have two hydrolyzable ions. And like I said, we won't be covering those. We'll just be doing one or the other. The calculations can be done fairly straightforward. And so again, they're just like what we've been doing so far. The only thing is that you have to find the Ka or the Kb for the ion that hydrolyzes. And we just saw how they're related. If you want the Ka for a positive ion, and you can't find it, you can find the Kb for the base and calculate Ka. Or if you want to find the Kb for a negative ion, such as the acetate ion or the Cn negative ion, you can look up the acid, the Ka for the acid, and then find the Kb by calculation. And so we're going to do an example that will go through this, this idea. All right, so what is the pH of a 0.1 molar NaCN solution at 25 degrees? The Ka for HCN is something you could look up. It's 4.9 times 10 to the minus 10. Okay, so when you're looking at this, you see that, okay, NaCN is definitely a salt because there's a positive ion and a negative ion, neither of which are H plus or OH negative. However, both of the ions will come from an acid or a base. So the first thing you want to do is analyze the salt to figure out if it's going to be acidic or basic. So we know that sodium cyanide, when it breaks apart, gives us the Na plus ion. Na plus is from one of the 6 strong bases, and so it's not hydrolyzable, so we can ignore the Na plus. The Cn negative ion, as we've seen in earlier examples, does hydrolyze. The Cn negative acts like a weak base. It will accept a hydrogen when it's dissolved in water and will produce OH negative. Okay, so we know that this salt should be somewhat basic because it has the Cn negative ion. But what will the pH be? We can calculate that. Now this is just a regular old base problem like we've seen before. You have a base plus water gives us a conjugate acid and OH negative. So we know that we can use the Kb expression to find OH negative and then find the pH. So the only difference is that we don't know the Kb value because we can't just look it up for Cn negative. The only thing we've been given was the Ka value. So we just remember that Ka times Kb equals Kw. So Kw divided by Ka gives us Kb. So here we've done the calculation. So Kb equals 2 times 10 to the minus 5th. Once we have that, the problem is just like any other that we did earlier in this chapter. All right, so now we know what the Kb is. So here's our hydrolysis reaction. Cn negative plus H2O gives us HCN plus OH negative. We know that we can set up our ice chart. So we know that the 0.1 molar Cn negative, we have 0 HCN and 0 OH negative. And then some of the Cn will negative will hydrolyze, so we'll call that X minus X, and then on the other side plus X. And then 0.1 minus X is our base concentration at equilibrium, and X is our HCN concentration and our OH negative. Plug that into our Kb. So there's our Kb expression. HCN times OH negative divided by Cn negative equals Kb. We have the Kb value now, 2 times 10 to the minus 5th. And it equals x squared over 0.1 minus x. We can do the same thing that we did before, where we can take the Cb 0.1 divided by Kb, 2 times 10 to the minus 5th, and we find out that that's 5,000, so that's definitely much greater than 100. So that means we can drop the minus x in the denominator. So now if we solve this, we have x squared over 0.1 equals 2 times 10 to the minus 5. Multiply both sides by 0.1, so we'll have x squared equals 2 times 10 to the minus 6. And if you take the square root of that, you get 1.4 times 10 to the minus 3. All right, so x, which equals OH negative, is 1.4 times 10 to the minus 3. And so the pOH is 2.85 or 2.8. If you subtract 2.8 from 14, you get 11.2. So the pH of this solution is 11.2, which is basic, just like we expected it to be. So remember that the main dish is this is just like a regular weak base problem. The only difference is when you look at NaCN, you may not see right away that it's a weak base. You have to evaluate the salt to see if one of the ions is acidic or basic. And then the only other thing is that because it is basic, you have to have the Kb, but you're given the Ka, so you'll have to calculate the Kb. And that's really the only difference between this problem and one of the earlier problems that we did.